Today we're going to do Module 8, Lecture Notes 15. We left off last time talking about electron configurations, okay? And that was the electron configuration for an individual element, like bromine. Today we're going to look at how individual elements can react with other elements to form compounds, which is sometimes called molecules. How the electrons actually interact with each other in an atom to form compounds together. So let's do a quick review of how we got to the electron configuration of bromine. I have my periodic table from last time, and remember, it's often helpful to look at where you're trying to go. We're trying to get to bromine. We always start at the top like we're reading a book, and remember the rhythm that we had going. Okay, so if we say this together and you say it out loud as you're taking these notes, we would start up here with the 1s. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, this is 3d10, and then it goes back to 4p, 1, 2, 3, 4, 5. We would end with 4p5 for bromine. So that's how I got this electron configuration for bromine that you see on your notes. Off to the side here, I have drawn what the electrons in those orbitals around bromine would look like. We know that bromine is element 35, so there should be 35 electrons moving around the nucleus. And I wrote here that the electrons are in energy levels 1 through 4. And I know that because this large number out in front tells me the energy level. So if you want to circle those and write energy level. That corresponds to the row on the periodic table. We made it all the way to row 4 or energy level 4 to get to bromine. Okay, so let's break down which electrons are in which energy levels for bromine. If we start with energy level 1, I have the 1s2. These electrons here, these 2 electrons, are in the 1s2. And you can see that in the picture. In the innermost energy level, I have these 2 electrons. Going to the second energy level, we're going to look for anything that has a large number 2 out in front of it. And notice I have 2s2, but I also have the 2p6. So that would be a total of 8 electrons in the second energy level. And if you count these in the second ring, there should be 8 of them. Moving on to energy level 3. See if you can gather all of the energy level 3 electrons from my electron configuration. I found the 3s2, the 3p6, and I also have 3d10. So that gives me a total of 18 electrons in energy level 3. And for energy level 4, I just have the 4s2 and the 4p5. And that would be 7 electrons. And if you count in the outermost energy level, there should be 7. Now, why do we care about which electrons are in which energy level? Well, when atoms come close to each other and they try to interact, only the electrons in the outermost energy level are able to interact with one another. And that would be energy level 4. So these electrons here are the ones that are going to form compounds with each other. These are called valence electrons. And you might just write that they react to form compounds. And I've written that here below. The electrons in the outermost energy level, the farthest away from the nucleus, are the ones that form compounds. And if you think about that, the ones that are really close here to the nucleus, they're held in pretty tightly. Okay, your nucleus has a positive charge, your electrons have a negative charge. They're zipped up pretty tightly to the nucleus. But the ones that are further away from the nucleus, they're not being pulled in as much. So they have a little bit more free reign to start to interact with the things around them. And that's what we're going to focus on today. Okay, down here in this section, I've given you 4 elements. And I'd like you to take a quick second and count up how many valence electrons each of those have. I will do the first one for you. Remember, valence electrons are the electrons in the outermost energy level. So if I'm looking at fluorine, I see that the outer energy level, or the highest energy level, is 2. I have 2s2 and 2p5. That is a total of 7 valence electrons. I only care about the ones in the outer energy level. I'd like you to go through these next 3 examples and count up how many valence electrons each of those have. You should have gotten 7 for all of these. They all have an S2 and a P5, making a total of 7 in the outermost energy level. What you'll notice about fluorine, chlorine, bromine, and iodine is that they all belong to the same column on the periodic table. They're all right here: fluorine, chlorine, bromine, and iodine. And we said that they all happen to have 7 valence electrons. Well, it works out nicely that the column on the periodic table tells you the number of valence electrons. Okay, so on your nice periodic table that you have, you can go through and you can bold or make these column numbers larger, because that tells you the number of valence electrons. All of the elements in column 3 will have 3 valence electrons. Column 4 have 4 valence, so on and so forth. And so that means that those elements in the same column, they're going to react the same way. They're going to have similar properties because they belong to the same family on the periodic table. Now there's one special family on the periodic table that I want to take a second to talk about, and that is the noble gases. Okay, and if you remember, they are right here. They are the last column, and they have 8 valence electrons. Their s and p orbitals are all the way full because the s is full and the p orbital is all the way full. This is ideal, okay? So they rarely undergo chemical reactions, and the word for that is they are inert. They don't really react with many other things, and they don't need to because they have full electron shells. They're happy the way they are. Their outer ring is all the way filled up, so they don't need to borrow an electron from a neighbor. What's also important is that the other atoms on the periodic table strive to be like the noble gases. They want full valence shells too. Okay, so that brings us to this special rule. It's called the octet rule. And think of the word octet meaning 8. everybody wants 8 valence electrons to be stable. So all the other elements are trying to fill up their electron shells to be like the noble gases who have 8 valence. The only exception is that hydrogen only wants 2 electrons. Because its nearest noble gas is helium, right here, and it only has 2 electrons total. So that's just a little exception there. Okay, so one thing we're going to learn how to do today is to represent the number of valence electrons with dots. And this is often called a Lewis dot structure. So for lithium, here in this column, we know it has 1 valence electron. It has 1 dot. Beryllium should have 2 valence electrons. It's in column 2. So it's going to have 2 dots. Boron, following the pattern, has 3 dots. And you can see that I'm giving the element 1 dot on each side, each of its 4 sides. Then, if it has more than 4, you're going to start to double up. So, for example, nitrogen, it has 5 valence electrons. 1, 2, 3, 4. Then I put a second one on the right side. Oxygen would look like this, with 6. And fluorine would have 7. And neon would have 8 total. Give 1 to each side and then double up. Okay, I would like you to try these 2 elements on your own, gallium and tellurium. Gallium is right here, and it has 3 valence electrons because it's in the 3rd column. So I would go 1, 2, 3. 3 valence. And tellurium is here, Te. I look up and see it's in group 6. 1, 2, 3, 4, 5, 6. And that's how you do Lewis dot structures. All right, so what Lewis dot structures help us do is they help us see how to fill that valence shell to be like the noble gas that's all the way full. All right, so let's start forming some compounds. Do you guys remember what ionic compounds are? They are compounds that have a metal, remember, an element from the left side of the periodic table, and a non-metal, an element from the right side of the periodic table. Remember that? Our dividing line, we need 1 from the left to react with 1 from the right to form an ionic compound. So let's look at a really simple compound that we use all the time. Let's look at table salt, like the salt that you put on your food at dinner. Na and Cl. Sodium is in column 1, so it has 1 valence electron. Chlorine is in column 7, so it has 7 valence electrons. Look at this like a puzzle. Chlorine really wants to finish its valence shell. It is so close to being like the noble gas argon. It only needs 1 more electron. Well, perfect. If it bonds with sodium, it can get that last electron and have a full valence shell. Well, some of you might be saying, well, then sodium won't be happy. Actually, it will. The ones in this 1st and 2nd column, and even the 3rd column, it's easier for them to lose an electron and go backwards to be like the next nearest noble gas than to gain a whole bunch of electrons to be like the next noble gas. So they're going to do whatever's easiest for them. And in this case, it is easier for sodium to give its electron to chlorine to make both of them happy, like the nearest noble gas. So go ahead and show that. Sodium gives the electron to chlorine. And you can even write wants to be like noble gas to help you remember what's happening. In ionic compounds, the rule is going to be that the metal always gives electrons and the nonmetals always take electrons. Or another way to say that would be lose and gain. This is so that they each end up with 8 full electrons in their highest energy level. Okay, when an element loses electrons, it becomes an ion. When an element gains electrons, it also becomes an ion. An ion is a name for an atom that has either gained or lost electrons. It is not neutral anymore. When you lose electrons, you have a positive charge. An element that gains electrons has a negative charge. Okay? The way that I like to remember this is like friends. Remember that electrons are negative. If I lose a negative friend, I tell them, hey, I don't want to associate with you. We're not going to be friends. You're being negative. I'm going to become a more positive person. If I gain negative friends in my life, if I have negative people around me, I'm going to become negative. And so that's just the way that I tend to remember how the charges are formed. Okay, and so I just wrote that little story here for you. I lose a bad friend, I become positive. I gain a bad friend, I gain an electron in my life, I'm going to become negative. Okay, and so hopefully that helps you remember it. So let's jump into an example of ionic bonding. I'm telling you I want magnesium and fluorine to bond with each other. Your first step is to go to your periodic table and write down your symbols for magnesium and fluorine. Then you're going to look and see how many electrons magnesium has in its valence shell. And it's in column 2, so you would draw it with 2 valence electrons. For fluorine, it's in the 7th column, so it should have 7 dots around it. Okay, then you're always looking for how your metal, like magnesium, can get rid of its valence electrons. And I see that if I go like this, magnesium can give 1 away to fluorine, and that makes this fluorine full and stable. But where can it give its other 1 to? Magnesium and fluorine are bonding with each other, so I can't add any other elements, but I can add another fluorine with 7 valence electrons. And it can give its to fluorine here. Magnesium gives 1 electron to each fluorine. Now everyone's happy because they all have full valence shells. Your last step is to think about the charges. If I get rid of 2 negative friends in my life, I'm going to have a +2 charge. Each fluorine gained a negative friend, so they should have a -1 charge. They gained 1 electron each. To write your formula for magnesium fluoride, you need 1 magnesium, and it took 2 fluorines to solve this bonding picture. So my final formula for magnesium fluoride would be MgF2. That's what you would need to do to fully solve this example. Draw it, show where your electrons are going, show your charges, and then write your final formula. I always try to give you guys a way to check your answer, and the way to do that on these is to make sure that your charges add up to 0. If I have 2 positives, I should have 2 negatives in my picture, and then I know that I've done this correctly. Go ahead and try potassium oxide on your own. For potassium oxide, potassium has 1 valence electron and oxygen has 6. So I know that potassium's going to give 1 away there, but oxygen still really needs 1 more to have its full 8. So I need to create another potassium. They each give 1 away. When I add my charges, the metal is always positive. Each potassium got rid of a negative friend, so they are positive. Oxygen gained 2 negative friends. Make sure you have the same number of positives and negatives, and then you're going to write your formula. It took 2 potassiums to 1 oxygen. K2O would be my formula. All right, I have my last example set up. Aluminum has 3 valence, sulfur has 6. Remember, the metal is going to give away its valence electrons. Sulfur needed 2, and it was able to get 2 from aluminum. It's happy. I still have 1 left that aluminum needs to get rid of to be like the next noble gas. Where can it go? The only thing you can do in this problem is to create another sulfur with 6 valence electrons. And it can go over to this sulfur. Oops, I drew too many on there. Sulfur only starts with 6. So what you should see is this sulfur still needs another valence electron. And so we're going to need to create another aluminum that comes in with 3. Goes there. And I have 2 left over. So the last piece to your puzzle is to create a 3rd sulfur. And aluminum can give away there and there. So for this to work out, you're going to need 2 aluminums and 3 sulfurs. When you look at your charges, your aluminums always gave away 3. So they are positive, and each sulfur gained 2. So they would have a -2 charge. You can check to make sure you're neutral. I have 6 positives, 2, 4, 6 negatives. And your final formula would be Al2. It took 2 aluminums and 3 sulfurs to work this one out. Okay, I'd like you to pull out your periodic table, and we're going to write a couple patterns on here that I think you'll start to notice. At the top of column 1, all of these elements want to get rid of their valence electrons, so they will always take on a +1 charge. They're going to get rid of 1. Same thing for column 2. They prefer to lose 2, so they're going to be +2. Column 3, you're going to put a +3. Okay. Let's jump over here to the noble gases. They tend to be happy the way they are, so they're not going to really react with anyone. You can put a 0 above them. Column 7, they like to gain 1, so they're going to have a -1 charge when they gain an electron. -2, -3, and these elements right in the middle, they can either lose 4 or they can gain 4. It's the same amount of work each way, and it kind of just depends on who they're reacting with. So I like to put +4, -4 for that column. Okay, so what I've written for you here at the bottom is that there's some rules you can read through in your book about those charges, and you do need to know those for quizzes and tests. Your quizzes and tests, you will be given a periodic table, but it will not have these patterns written here for you. That is something that you need to know in your head, how many columns and how many electrons like to be gained and lost before you come in to take your quiz or test in your class. All right, so this is a lot of work to draw this out every single time you want to bond two elements together. So let me show you a quick shortcut. Yay. All right, so all you have to do for this shortcut is you're going to look up the charges on your periodic table that we just talked about. So if we're doing sodium bonding to nitrogen, sodium nitride, you find sodium, it likes to be a +1. Nitrogen likes to be a -3. Okay, so what you can do is write sodium +1, nitrogen -3, and you're going to crisscross these charges. And you end up with Na3 because I crisscrossed my charges. Na3N. The superscripts or your charges come down to the bottom, and then you drop the plus and the minus, and that is the shortcut for writing an ionic formula. Let's try another one. Magnesium bonding with phosphorus. So you're going to look up your charges from the column on your periodic table, and you're going to flip them. Mg3P2. So that means you need 3 magnesiums to bond with 2 phosphoruses to make a neutral compound. If you were to draw the electron dots, it would look something like this, but it saves you a lot of work by just flipping the charges. All right, and the last one I want you to do is calcium bonded to oxygen. Calcium is in column 2, so it likes to lose 2, and oxygen's in column 6, so it likes to gain 2. If you get 2 charges that are the same, you are going to reduce if you can. So this would reduce to just CaO. All right, so if you flip over to the back of your notes, you'll notice I talked about some exceptions. We have not talked much about this middle block of metals. These are your transition metals. They contain a lot of the metals that you're familiar with, things like copper and zinc and nickel and silver and gold. But they do not follow the same bonding pattern each time. They're metals, so they will lose their electrons. But sometimes they lose 1, sometimes they lose 2, sometimes they lose 3. There is not a rule that we can assign to this entire block, and so we don't. So how do you know how to bond them? Well, with transition metals, we use Roman numerals. The Roman numeral tells you the charge on the metal. So that actually is pretty handy. Let's look at this first example. Tin is the symbol Sn. It's found right here on your periodic table. This Roman numeral 2 is telling you that tin likes to have a +2 charge when it bonds with chlorine. So you get your charge on your transition metal from the Roman numeral. For chlorine, you can get it from our column rule. It likes to be a -1. The crisscrossing works the exact same way, and you end up with SnCl2. Okay, so it's not hard. You just need to really pay attention to the Roman numeral. Here, tin is bonding with chlorine, but in this case, it likes to be a +4. That is the Roman numeral 4. So you're going to crisscross, and you end up with SnCl4. Okay? Go ahead and try the last one on your own. Okay, manganese 3 bonding with oxygen, and this would be my ionic formula. Thanks for listening.